Hello, good afternoon.
Good afternoon, sir.
Yes, good afternoon. Good afternoon to all. In the previous class, we started module 3, Introduction to Embedded System. And here we understood the definition of system first. So you got to know what is a system. So collection of interrelated components that work together to achieve some common goal. Okay. And then we understood what is embedded system is, which is an electronic or electromechanical system designed to perform a specific task. So using both hardware and firmware. And then we looked into the examples of variety of examples of the embedded system. Then we also understood every embedded system is unique in nature, and we also understood that embedded systems are inevitable part these days. So, through the embedded system, uh, so we are performing the computing everywhere, and that is called as one more field of computing, ubiquitous computing. That is, the computing is everywhere. So you cannot list the uh, domain or the area where there is no computing. Computing is everywhere. So wherever embedded systems are there, so computing is there. Okay. And then we looked into the IEEE definition of embedded system. So IEEE defined it as a device that is lodged or housed in other systems to perform some specific task. Then we looked into the important characteristics of the embedded system. So very major and important characteristics. So after that, yeah, from here we got to start. So now, so let us try to understand the differences between the embedded systems and the general computing systems. So first, these are the key areas on which we understand the differences between the embedded systems and the general computing system. So first, we'll try to understand based on the contents. Okay. Now, if I take a general purpose computing system, which is your normal desktops or the laptop computer system, so it is a combination of generic hardware and general purpose operating system. So why we say generic hardware? Because the hardware here is the more generalized one, which can be used for performing any type of computation. And the operating system is also general purpose operating system, or short form you can also call it as POS, platform operating system. Okay. For executing variety of applications. So a general purpose computing system consists of a general hardware or a generic hardware with a general purpose operating system, which allows you to perform the execution of many different types of applications. So that is what is the content of a general purpose computing system. Now if you look at the other part, so embedded systems, okay. So it's a combination of, it is not a generic hardware, instead it is a special purpose hardware. So the hardware which is designed or developed to perform only a specific task. Okay, it's a combination of a special purpose hardware and an embedded operating system for executing a set of applications. So for executing a specific set of applications, again, it is a set of applications. You cannot have wide range of applications. So as it was here, executing variety of applications, so only a set of applications can be done. So sometimes an embedded systems will be designed to perform only a specific type of application, and sometimes they are designed to perform set of applications also, and but not in general. Okay. So they have a special purpose hardware. So whereas these things have a generic hardware and a general purpose operating system, and they have an embedded operating system. And the majority of the time, the embedded operating system is RTOS, real-time operating system. So this is the difference as far as the content of the general purpose computing system and an embedded system is concerned. Next, operating system if we take. So this we have already discussed here. So the operating system that is running on the general purpose computing system is GPOS, that is general purpose operating system. So that is what is mentioned here. Or just even shorter, you can also call it as platform operating system. So, but if I come to the embedded system, so majority of the time it is real-time operating system, and sometimes an embedded system may not even contain the operating system also. If the function of an embedded system is very specific and very simple, then the embedded system need not even contain the operating system. Only the bootloader code and the firmware which is present inside the ROM is sufficient. That is the reason we say it may or may not contain an operating system for functioning. And next, so this is with respect to the uh, operating system. So alterations. So applications are alterable in case of general purpose computing system. So that means any number of time it is possible for you to install and uninstall and reinstall. All these things you can do. So because they are programmable. So that is what is the advantage of general purpose computing system. Okay. So applications are alterable. That means programmable by the user. So it is also possible for the end user to reinstall the OS and also add or remove the user application. Any number of times you can do this, and that is what we people are doing on the laptop or the desktop system. So whenever I require some application program, I go for installing it, and whenever it is not at all required for me, then I go for uninstalling it and go for requiring installing one more other application which is very much essential for me right now. Okay, so this is and if I go to the embedded system, it uses something called as a firmware. So the software is a firmware here which is permanently residing inside the read-only memory, and it cannot be altered by the end user. So once the embedded system is manufactured for performing some dedicated task, throughout its lifetime it has to perform the same task, and it is not possible for you to reprogram it and perform the embedded system, make the embedded system perform a different task. So that is not possible. Okay, so hence we call it as the firmware here. So hope you people are able to understand. Hello.
Yes, sir.
Okay. Next is the third important thing that we are going to discuss. The differences is key factors. So key factors in deciding the selection of the system. Say for example, I want to buy a laptop or a desktop system. So what are the key factors that I'll be looking in before purchasing a laptop or a desktop? So performance is the key factor that I look in. So I always go for buying a laptop or a desktop which provides a very good performance. Okay, that is what is the key deciding factor. So in the selection of a general purpose computing system, and always we go for choosing the faster one. And similarly, so if I go for the embedded system, so I look into the application specific requirements like performance. So here, when you are deciding on the embedded system, it is not only the performance. So we also look into the power requirements, memory usage. So these are the three main key factors that we look in while choosing or selecting an embedded system for what buying. So, but here in the general computing system, the desktop or the laptops, so we always only focus on the performance key factor, but the power requirements and memory usage we don't focus, because generally the desktops and the laptop systems comes with a huge memory now, so 1 TB, 2 TB. So, but here the embedded systems always they'll be having the limited memory, and even any embedded system which is consuming more power we don't prefer. So if it says it has higher performance also, we don't prefer it. So because it is consuming more power. So now the key deciding factors for deciding which embedded system to buy is the performance, power requirements, and memory usage. All the three you should take into account and then go for making the decision. So this is the fourth difference. And the fifth difference is with respect to the power consumption. So the power consumption here is more. on the general purpose computing system, because while selecting the system itself, we have not focused more on the what power issues. So our focus only on the performance of the computer system or the laptop systems. Now here the power consumption will be obviously more, and then here the power consumption is less. So because it performs only one specific task, and it is optimized to do that task in such a way that it consumes lesser power. Okay. So this is the difference with respect to the power consumption. And then response time. Okay. So response time for the general purpose computing system is not that much critical. So response time, even if sometimes, even if there is some delay in the response time, nothing severe damage is going to happen. So, but when I say an embedded system, the response time is very important. So, especially for the embedded systems which are designated as critical embedded systems, the response times must be very good. So, say critical embedded systems, which I was mentioning in the previous class, heart pacemaker, insulin pump system, so anti-braking system which are used inside the car. For all these things, the response time must be very good. Even a small delay in response time for these types of critical embedded system will cause a severe damage. So that is what is the difference with respect to the response time. Okay, the response time for the general purpose computing system is not that much critical, but the response time for the embedded system, especially for the critical embedded system, it is very much essential. Next is execution. So need not be deterministic. Okay. That means, so whenever, say for example, in the general purpose computing system, say I'm running a task. So the execution completion time of the task so need not be deterministic. That means, say for example, I have a task and to execute, and that task uh, 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 requires 100 milliseconds of execution. So when the CPU is assigned to it, say it requires 100 milliseconds of time for completing its execution. So when the CPU is assigned to that process on the general purpose computing system, and if that process say performs execution for 10 milliseconds, so still 90 more milliseconds execution it has to go. But before that, say CPU is preempted from that process and given to the next process. Now, in 100 milliseconds of time, it has executed only for 10 milliseconds of time, and still it has to perform its execution for 90 more milliseconds, and it is waiting again for the allocation of the CPU. So now that's why, so we say once the CPU is allocated to a process, even though its execution time is 100 milliseconds, so we cannot assure that it's going to say if it is starting its execution at 10th millisecond, we cannot assure that it's going to complete its execution in 110th millisecond. So 110th millisecond. Why? Because in between the CPU will be switching from that process to another process. When the CPU is switching, so the process will sit idle. So with this CPU switching and all, so usually even if the execution time of the entire process is only 100 milliseconds, and if it is starting its execution at the 10th millisecond, there is no guarantee that it's going to finish its execution at 110th second. So the execution may even continue after that. So hence we say the execution of the processes or the execution time for the processes in case of the general purpose computing system is not deterministic all the time. But embedded system, so the execution time for a process or a task, it must be deterministic. Say for example, within an hard real-time system, I have a task to be performed, and that task T1, let us assume the task is T1, and that task is starting its execution at the 10th millisecond, and the total execution time of the task T1 is 50 milliseconds, and it is starting its execution at the 10th millisecond. Now by 60th millisecond, the task must complete its execution. So there is no delays entertained. Say instead of 60th millisecond, they say process so has delayed by 10 more milliseconds, and it is completing its 70 millisecond. So then there will be the threat cost. If it is a critical type of system, then there will be either threat cost to the human life or to the physical environment, or there will be an economic loss. Now, how to prevent all these things? By making the system hard real-time system. So once you make the system hard real-time system, So what does it mean when I say a system is all real-time system? It is running a real-time operating system. So now the real-time operating system is going to guarantee that all the tasks, so they are going to complete their execution within their specified time period without any delay. So that is what is deterministic with respect to the execution. And so here it is non-deterministic. Execution time is non-deterministic, but on the embedded system, you got to compulsorily make them as deterministic, especially in case of our real-time system. For soft real-time system, so there can be some relaxation on the execution time. Okay, so but for the hard real-time system, there is no relaxation for the execution time. If a task, if I say it requires 50 milliseconds of execution, and if it is starting its execution at 20th millisecond, so 20 plus 50 at 70th millisecond, so the somehow the process must complete its execution, or the task must complete its execution. That is the reason we say it is deterministic, whereas in case of the general purpose computing system, it is non-deterministic. And I hope you people are studying the operating system concepts now. If you go to the CPU scheduling algorithms, so there you'll understand. Okay, so when a process is located the CPU, it's not going to hold the CPU until it finishes its execution. In turn, what it will do, so the when that process wants to perform some input output operation, CPU simply switches to the next process and goes for performing the execution of that. So and this switching may um, is making the process execution time not deterministic or non-deterministic in case of general purpose computing system. So any doubts in this? Are you people able to understand all the how many differences? 1, 2, 3, 4, 5, 6, 7. 7 differences between the general purpose computing system and the embedded system. Hope it is clear to all of you. Hello.
Yes.
So, so the last one you understood. What is the meaning of deterministic? So here, the execution time in case of a general purpose computing system is non-deterministic, whereas here it is deterministic. It must be deterministic. So any doubts if you have here, please let me know before I go to the next slide. Okay, so all of you have understood it. Thank you. Next, history of embedded systems. So next, what we are understanding is the history of the embedded systems. Even we have the history of the computer systems also. So if I take the history of the computer systems, so the computers prior to 1945, they were all mechanical computers in which the computation and communication was done through moving mechanical parts. Okay, so in earlier computers prior to 1945, the all computation and communication was done through moving mechanical parts, and they were called as mechanical computers prior to 1945. So for the first time, from 1945, the modern computer started. The first electronic computer was invented in the year 1945. Hence, the computers from 1945 till now, they're called as modern computers. And again, those modern computers, the computers from 1945 to till now, are grouped into various generations. Say first generation computer, second generation, third generation, fourth generation, something like this. So even here also, and this is what we call it as the history of the computer systems, or the revolution of the computer system. Here also, there is an history for the embedded system. Now, when did this embedded system came into picture? So they came into picture even before IT had its place in the market. Even before the information and technology came into picture, so the embedded systems were there in the market. And initially, so what kind of devices were used in order to manufacture the embedded system? It was vacuum tubes. Even the modern computers, when they started in the year 1945, so the majority of the hardware component in the computers which were there in 1945 were vacuum tubes, because there were no transistors and diodes during that time. So the major components of the computer systems are vacuum tubes. So these vacuum tubes used to perform the role what now are transistors and diodes are doing that time. So vacuum tubes were used in order to perform that. Now how vacuum tubes looks, you can just Google this word, you'll get the pictures, plenty of pictures in the vacuum tubes. I forgot to put the one here. So but always you can Google and you can see how the vacuum tubes used to look. And these were the major hardware components that were used even in designing and building an embedded system. And what kind of a programming language that was used? So low level programming language. So low level programming language was the language that was used in order to build the uh, embedded systems. And then I will look into the uh, examples. Okay. So the first modern embedded system, so as I mentioned, the first modern computer system started in the year 1945. So similarly, so the first embedded computer, okay, was Apollo Guidance Computer, which was developed by Charles Stark Draper at MIT in 1960. Okay, and later in 1961, so this Autonetics D17 was developed, and the first microcontroller-based embedded system, so in the form of Intel 4004, was designed for the calculators. Even the calculators are also embedded system, but that time, so they were using the 4-bit microcontroller. So this calculator was designed using a 4-bit microcontroller. And next, even 1970s, so even this automobile started using the microprocessors. For what purpose? For controlling the fuel, air mixture, and then also for the engine timing. Okay, so in all these things, places we have the microprocessor used. And again, the first microcontroller TMS 1000 was developed in 1974 by Texas Instrument. And this TMS 1000, which was developed in the 1974 by Texas Instrument, it consisted of, see, everything, RAM, ROM, and clock circuitry also within the same chip. What is this clock circuitry? RAM, you know, we have already discussed. Random access memory or your the main memory. RAM is read-only memory which stores the firmware. And what is this clock circuitry? So as I was already mentioning, for a microprocessor or microcontroller to do any task, you got to supply the clock pulses or the clock cycles. And this clock circuitry is the one which is responsible for generating the clock cycles required by the microcontroller or the microprocessor. Now how it is going to generate? So this clock circuitry has a special device called as quartz crystal. So quartz crystal, they usually come in terms of 16 megahertz or 32 megahertz or 64 megahertz or 512 megahertz or 1 gigahertz or 2 gigahertz, something like this. So that quartz crystal oscillates with a well-defined frequency, and it is going to generate all the clocking requirements of the microcontroller. Okay, so and then in 1980, so Intel also introduced the microcontrollers. Okay, 8051 microcontroller, and this microcontroller was widely used in the laser and in inkjet printers. Okay, and so 1990s the small pagers started. So I don't know whether the people have noticed this pagers or not. I have seen this. So 1990s the small pagers came into picture, and after 1990s till 2000, so the small pagers were ruling the entire world. So and in the year 2000, so the cell phone started, and the moment the cell phone started, okay, came into picture. So even the sales of the cell phones far exceeded the sales of your desktops or the laptops. And from the year 2000 till now, it is the cell phones, whether the Android phones or the iPhones, uh, which are ruling the entire world now. Okay, so this is how the embedded systems have undergone the revolution, and from what the 1960s till 2000. So and now we are in 2021. Even today, it is the cell phones that are ruling the entire world. And what I can say is the sales of the cell phones now it has far exceeded the sales of the laptops or the desktops, because everyone has the smartphone and iPhone. So hope it is clear till here. Hello.
Yes, yes.
Yes.
Okay. Next. So with the understanding of a very brief history of classification of embedded system. So how embedded systems are classified? So they are classified from four basic classifications. So four basic classifications are made. One is classifying the embedded system based on their generations. So even I mentioned, even the computer systems after 1945 till now, they are grouped into various generations. First generation, second generation computer, third generation, fourth generation computer, fifth generation computer, something like this. Now, on what basis these computer generations were made? So these computer generations were made whenever there was either the sharp change in the hardware or the software technology. Similarly, even the embedded systems are also classified based on the generation. So we say first generation embedded system, second generation, third generation. So similar to the computer system, even the embedded systems are also classified based on the generation. Okay, so that is what we call it as generation-based classification. This is one type of classifying the embedded system. The other type of classifying the embedded system is complexity and performance based classification. Now, how the embedded systems are classified here? So by taking into account the complexity of the embedded system. What complexity? The software complexity and hardware complexity. So majorly, so by taking into account the hardware and software complexity, and also by looking into the performance of the embedded system, this classification is made. And the third classification is based on the deterministic behavior based classification. So in the earlier side, when we were discussing the differences between the general purpose computing system and the embedded system, so we understood a difference with respect to the execution. So there I said, so general purpose computing systems are non-deterministic, execution time is non-deterministic, whereas for the embedded system it is deterministic. Now, when I say deterministic, so again, there are two types. So hard real-time systems and soft real-time system. So classification based on that, if we call it as deterministic behavior-based classification, and trigger-based classification is also there. So these are the four basic classifications of embedded systems. So, but our focus will be on the first two. So we discuss first generation based classification and complexity and performance based classification, and we don't discuss this deterministic behavior based classification and triggering based classification. So, but we have a separate module for discussing on the real-time operating system. Okay, but we're not going to discuss this deterministic behavior based classification of the embedded system. Okay, we discuss only the first two classification, that is generation based and complexity and performance based classification. So hope it was clear the different types of embedded system classification. Hello.
Yes, sir.
Okay. Now, first we'll focus on the first type of classification. So generation-based classification. So this is what the generation-based classification. So we discussed this generation-based classification. So with respect to three things. So first, the generation itself. Next is description, very short description of the generation and an example. So first generation also represented as 1G. So if we look at so what kind of processor or a microcontroller the first generation embedded systems were using? So they were all using either 8-bit microcontroller, sorry, microprocessor or 4-bit microcontroller. And the examples for the 4-bit microcontrollers are also written here. So 80, 85 and Z80 were the 4-bit microcontrollers which were most widely used in the first generation embedded systems. Or if microprocessor was used, it was 8-bit microprocessor. And why since they were using only 8-bit microprocessor or 4-bit microcontroller, the hardware circuitry was very simple. Okay, and what kind of a language was used to write the firmware? So that is the software which is stored inside the ROM. So ALP was the language that was used. Assembly level programming language was the one which was used to write the firmware softwares. And where these things was most widely used. Few examples are given. So this 8-bit microprocessor or 4-bit microcontroller, they were most widely used in making the digital telephone keypads and also in the stepper motors. So stepper motor will understand more on this in the lab program. So we have a lab program, and we'll also be discussing more on these things in the theory session as well. Okay. And so with this, a very brief insight into the first generation embedded systems. So let us look into the second generation embedded system. So just observe what microprocessor, how many bit microprocessor they were using. They were using 16-bit microprocessor or an 8-bit microcontroller. Okay. So and these are more powerful than the 1G. Why more powerful? So by looking into the processor itself, we can tell. So this is 16-bit and this is 8-bit microcontroller or 16-bit microprocessor. Even the hardware circuitry also increased appropriately. And wherever this second generation embedded systems were most widely used, so they were used in data collection systems or the data acquisition systems, the systems which used to collect the data. Say for example, either it could be the weather data. So you make a system, embedded system, using a 16-bit microprocessor or 8-bit microcontroller, install them in the physical environment, so where it goes for sensing the humidity, temperature, all these things using various sensors. It collects the data and stores the data. Okay. And even ADC also, analog to digital converter. So when I say all this data, the weather data, so it is in the form of an analog data or the continuous data. So before storing, we got to convert them into digital data. So this was one side type. So ADC was one such system where the 16-bit microprocessor or 8-bit microcontroller were used in order to convert and store the data, analog data, in the digital format. Next is another thing is SCADA, that is supervisory control and data acquisition system. So which were again most widely used for what uh, reading the data or acquiring the data and storing them for industrial control applications. And the advantage of SCADA over ADC is that, so ADC, it collects the data, stores the data in the digital form, but it will not provide you any provision for viewing the data. So but SCADA systems, so they collect the data, they store the data, even they provide the provision for you to visualize the data. So any type of data. Okay. Either it could be any measurable data, you can go for visualizing. So this is very brief into the second generation embedded systems. Now the third generation embedded systems, if you look at, see, 32-bit microprocessors or 16-bit microcontrollers were used, and they were domain-specific processors. So why we say domain-specific processor? It is not the same processor that was used across all the domains. So the processor usage or the microcontroller usage used to vary from one domain to the another. So networking domain, one type. So home appliances, another type of processor, something like this. And examples are also given. For robotics, a different type of um, uh, what processors are used for robotics example. And then the fourth generation 4G. So what kind of processor were used was 16-bit microprocessor or 32-bit microcontroller. So even in the fourth generation embedded system, the concept of system on chip. So later we'll understand this. SoC it is called as system on chip, entire system on the chip. You have microcontroller, you have memory, you have RAM, everything you'll find inside one chip. And the multi-core processors also evolved. So and then they have a much complex hardware and powerful software. Okay. So this is very brief into the fourth generation and wherever these things were used. So 32-bit microcontrollers or 64-bit microcontroller used inside the smartphones, which is ruling the entire world now. Okay. And you can just imagine now. So I say a smartphone with 64 GB, 64-bit microprocessor or 32-bit microcontroller, it is almost with the same capability or the capacity as our desktops and the laptops. Even our desktops or laptops goes for using a 64-bit processor or a 32-bit processor, and the same thing even you can find inside the smartphones as well. So this is about the classification that is made based on the generation. So generation based classification of the embedded systems. Hope you people understood here.
Yes, sir.
Okay. So this is the first thing, and next is the second type of classification. So complexity and performance based classification. So based on the complexity and performance, so embedded systems are classified as small scale embedded systems, medium scale embedded system, large scale embedded system. So these large scale embedded systems are also called as sophisticated embedded systems. Okay, you can also call them as sophisticated. Now we'll see what are small scale. So small scale or embedded systems are the one which either use an 8 or 16-bit microcontroller, and they have very less hardware complexity or little hardware complexity, and the software complexity also. Okay, and small, very small software complexities. So tools used for the development of embedded systems, the small scale embedded systems involve the small editors for writing the program, so assemblers for translating the programs into the machine code, or sometimes the IDE also, integrated development environment. So the key which we were using earlier for executing the program is an IDE. It is an integrated development environment. Why we call it as an IDE? Because everything is integrated there. So you have an editor. Say I'm not using a separate editor. So when I was using the key, so it was not a separate editor that I was using in order to write my program, and I was not using a separate assembler, and I was not using a separate debugger. So everything was found inside the same integrated development environment, that is Keel. So what is why we call it as an integrated? Because so editor is one tool, assembler is another tool, debugger is another tool. So all these things are integrated and made as what one environment. When you integrate several such tools, it becomes an environment. So that is what is called as integrated development environment. And Keel is one such integrated development environment. So where it provides you the editor for writing the program, where it provides the assembler for translating the program, where it provides the builder for building and linking the various libraries to your program, and a debugger where you can go for debugging the program. Okay, and even more it provides. So Keel also provides other things, where you can go for generating an X file and loading that X file onto the microcontroller. All these things it provides. So this is very brief into the small scale embedded systems. Medium scale. So medium scale uses 16 or 32-bit microcontroller. Okay, and they also adopt the features from the RISC design philosophy, so which we have understood in our first module. So even we understood that the ARM has adopted certain RISC features. So in general, any embedded system which is based on a 16-bit or a 32-bit microcontroller also is implementing certain features of the RISC design philosophy. And even so this my embedded systems which are based on 16 or 32-bit microcontrollers are capable of performing DSP processing, digital signal processing. Say for example, so they're specialized and they are capable of processing the audio signals, video signals, etc. All these things they can process it. Now, if we look into the hardware and the software, so they have appropriate level of hardware and software complexities. But the complexity of the hardware and software here, it is too low. So here it is more higher than compared to the small scale embedded systems. And what were the tools that were used here for developing the application? So I said here we were using the assembly level program. Okay. Now here we started using this C, embedded C, C++, Java, Visual C++, and the RTOS operating system. So these were the tools used, and simulators we were using IDE. So now we don't have to use a separate simulator. So because the key IDE which we were using, it is also a simulator. And then sophisticated embedded systems. So they use 32 or 64-bit microcontroller. So they have not just a moderate level of hardware and software complexities, they have a massive hardware and software complexities. Why we say massive? Because the hardware components which are used here, so they all have greater complexities. Okay, so the all hardware components used are here are sophisticated hardware components with greater capabilities, and similarly is the software. And where we use such sophisticated embedded system, they are used in high performance mission critical systems. So where so examples for high performance medical mission critical systems, say these are the examples. So they are used in flight landing gear systems, satellites. So this is car parking systems, military applications, robots. So these are some of the high performance mission critical systems, and that is where our large scale embedded systems or sophisticated embedded systems which are based on 32 or 64-bit microcontroller is used. And these systems, okay, the embedded systems, which we call them as sophisticated or large scale, so they also uses ASICs, that is application specific integrated circuits. So all of you know what are integrated circuits. There is something called as application specific integrated circuits also. So later we'll be understanding more on these things, and then PLAs also. So that is programmable logic arrays, which is a collection of AND and NOR gates uh, mm, designed and connected as per the logic required. So we are going to understand more on this ASICs and PLAs in future. Okay. So this is about very brief into the sophisticated embedded systems. So till now we understood the classification. So two classifications we understood: generation based classification, and then classification that is done based on the complexity and performance. So next is, so any doubts till here? So don't ask me what is this application specific integrated circuits and PLAs. So it will come in the future. Okay, I'll explain there. Understood till here?
Yes, sir.
Okay. Next, so major application areas of the embedded system. So where these embedded systems are used. So the domain where embedded systems are used is countless. So almost all the domains you'll find the use of the embedded system. And we are going to discuss now a few important domains and also the examples for the products, embedded systems which are used in each of the domain. So the first domain where the embedded systems are most widely used is the consumer electronics. So all these things, your video games and then camcorders, all these things are what consumer electronic devices. Okay, and these are all the embedded systems. And the another important domain where the embedded systems are most widely used is household appliances. So you can see the television is one embedded system, again DVD players, washing machine, refrigerator, microwave ovens. So all these things are again what the embedded system. This is another important domain where we go for using the embedded systems more widely. So and next coming to the next one, so home automation. Okay, so I want to make my home smart home. That is what is home automation and security systems. So even there, the embedded systems are used. So air conditioners, so which helps in home automation. Okay, and then the sprinklers, intruder detection alarms for security system, closed circuit television cameras. Okay, that's CC cameras. Okay, fire alarms. All these things. What are they again? So they are again embedded systems. Okay. So, and again, all these devices, air conditioners, sprinklers, intruder detection alarm, All these things, they are made smarter. Okay, so even when you're not there, so they're capable of managing on their own and gives you an appropriate alert message. Next is another important application area of embedded system is in the automotive industry. So it is most widely used in the automation industry also. So in the form of ABS, that is anti-lock braking system. So cars have ABS systems. Okay, so engine control. So all these days the people were using the vehicles to travel from one place to another place, and the people were not knowing that there is an embedded microcontroller or microprocessor present for controlling the engine as well, controlling the ignition system and automatic navigation system. So car I've put here, okay, and even in the train, okay, so it's there. So, and even in the earlier slide I told embedded systems, okay, so there even in the flights also to receive the signals, radar signals, and they are in and they are there in what the flight landing gear systems also. Okay, next. So this is with respect to the automotive industry. So now we'll go to the telecom domain. So even telecom domain, it is more widely used. So cell phones, telephone switches, handset multimedia applications. Okay, so all these things. Next, so even the computer domain also uses. Okay, so majority of the computer peripherals like printers, scanners, fax machines, so they have the microcontroller present inside them. Okay, not only the computer peripheral domain, look at the computer networking systems also. Networking domain. So even there in the network routers, it is there. Inside the switches, it is there. Inside the hubs, it is there. This is what you're seeing is a switch. How many port switch it is? 1, 2, 3, 4, 5, 6, 7, 8. 8 port switch it is. I guess the people have seen these types of devices. So, and this switch, 8 port switch is available in my staff room. So I have this with me. Okay, so printer is there, and then firewalls. So all these things. Okay, and again, so using some form of microcontroller or microprocessor inside them. Okay, come to the next one more important domain, healthcare domain. So healthcare domain, majority of the devices are there. So but all of them are not listed here. So scanners, so many different types of scanners are there. In every scanner you find a sophisticated microprocessor. It comes to the category large scale embedded system or sophisticated embedded system because usually they come with 64-bit or 32-bit microcontroller, EEG missions, ECG missions, etc. All these things are again what based on the microcontroller or microprocessor. So forget about this healthcare. Okay, come to this measurements and instrumentation. So we use many device for measuring purpose. Say digital multimeter, all of you are familiar with this. So previous semester people were using this for measuring the resistance, measuring the voltage, measuring the current, okay, all these things. So again, when I say voltage, DC voltage, DC current, AC current, all these things. Okay. So that is also an embedded system. Even it has a microcontroller inside it. And what about CROs, digital CROs, which you are seeing here, also has what? The microcontroller. And there is something called as logic analyzers, PLC system. So programmable logic control system. So I think picture is not there. So even those things are also what the measurement and instrumentation systems. So forget this instrument measurement and instrumentation. So take the banking and retail. So ATM, automatic teller machines, are also what the embedded systems. So currency counters or the note counters machine, okay, is also an embedded system. POS machine. So the POS machines which are used at the outlets. So where you give your credit card or the debit card, and the machine which is used for taking the money. Okay, POS, it's called as point of sale machines. And then the card readers also. So you go to the ATM, you insert your card, it reads the card. That is also an embedded system. So either it could be a barcode reader, smart card reader, handheld devices. So these are all. So around 11 domains are listed here with few examples. So there are many domains like this. So the major 11 domains are listed. So but still you can go for listing many more. So people understood till here?
Yes, sir.
Okay. These are the major application areas of the embedded systems. So around 11. So if you're asked to explain the major application areas of the embedded system, so don't restrict it to only 11. So if you know other application domains where the embedded systems are used, you can write them also as well. Next. So after understanding the application areas of the embedded system, next thing is what is the purpose of the embedded system? So okay, so many application areas are there. Now what for we are going to use the embedded system in all those application areas? What is the purpose? Okay, so that is what. So the purpose are is many. Sometimes we use this embedded system in the domains for collecting the data, storing the data, representing the data in some form. Sometimes we use the embedded system for data communication. Okay, sometimes we use the embedded system for doing the digital signal processing. Okay, or you can say data processing in simple. For monitoring purpose, majority of the devices which are used in the healthcare domain are monitoring devices. Okay, so they monitor your heartbeat, they monitor your BP, they monitor your sugar. Okay, all these things. And then control systems are also there. So they only go for monitoring. So for example, heartbeat monitoring system, it only monitors the heartbeat and says what is the rate at which the heart is beating. So but it cannot control the heartbeat. So there are other devices which can also do that. So heart pacemaker, I said, it's able to control and stimulate the heart beating. And similarly, some application specific user interfaces are also there. So these are some of the important purposes of using the embedded systems in the various application domains. Now, each one of these things we are going to discuss in detail. So now let us stop here and we'll have a detailed discussion. So on these things, purposes of the embedded systems in the tomorrow's class. Hope you people understood till here. Any doubts? Hello?
Yes, sir.
Uh, Understood? Okay. So now the next three modules, complete module 3, module 4 and module 5. It is like this only. So you will not get the programs. So no programs here. It is only the theoretical description of the module 3 is completely an introduction to embedded system. Module 4 is on the components of the embedded system and module 5 is on the real-time operating system of the embedded system. Okay, so let us stop here. So if you have any doubts, please feel free to ask me.